In this lecture, we're going to go through an approach to counting the electrons in a transition metal complex. Now, what I want to start by talking about is the fact that there's actually two very popular approaches to counting electrons around transition metals. There is, so let's get some notes already. So counting electrons in a transition metal complex. There are two popular approaches. I'm going to first mention the one that we won't be going through right now, and that's the oxidation state approach. Okay, the oxidation state approach. And here what you do is you take the electrons from the metal, and what you'll do is you'll kind of then subtract minus the oxidation state of the metal. And then it's plus the ligand electrons. And the ligand electrons come with kind of a star here because we'll use the ligand electrons with the oxidation state, which I'll label as OS method. Okay. So that is one approach, but it's not the approach that I am going to at least lead in with. I'm going to instead lead in with the neutral atom method for counting electrons. The neutral atom method. I would recommend mastering one of these approaches, or getting at least good enough to solve the problems. And then if you're super interested, go back and learn the alternative method. Obviously, if I'm going to focus on the neutral atom method, you all probably will too. The issue is there's like a really subtle way in handling the oxidation state electrons and the charge electrons. And what happens is you get a really subtle difference in how some of the ligands get counted. So there's an issue with the front end, and then there's an issue with the ligands that makes them different. So it's not like a super small thing that's different. But anyway, what we have here is we're going to take the electrons from the transition metal element. The electrons from the transition metal element. We're then going to add the electrons from the ligands. And now the electrons on the ligands are going to be counted using the neutral atom method. And then you're going to subtract the charge of the complex. Okay. Now, what's important about getting this one right, and really both of them right, is you need to be able to differentiate counter ions from ligands. And that will come with practice. It's not too bad. It's just one of these things where, like, right away you might be like, okay, I've got this formula. And then all of a sudden it's like, wait, why did I get this one wrong? And it's probably thinking that a counter ion is a ligand or something, which will throw everything off. Okay. So already we've already bitten off a lot here. So let's go ahead and look at some examples of this. So again, we're going to focus on the neutral atom method, which means the electrons in the complex. These are the electrons that we use to see if we've violated or followed the 18 electron rule that we talked about last time. So we want to see if electrons are going to get up to 18 or not. So this is kind of our our rule to get to that number. And so to see if we have 18 or 16 or something. What I want to do is start off with the classic transition metal complex that's really important for organic synthesis. and that's palladium tetrakis triphenylphosphine. Okay, a bunch of words to describe this complex. Okay. If you, and this is often called tetrakis because the name is palladium tetrakis triphenylphosphine. The tetrakis comes from the fact that we have 4 ligands surrounding the palladium that are triphenylphosphine. If we had tetra triphenylphosphine, that would be confusing. So tetrakis tells us that those triphenylphosphines are each ligands. So triphenylphosphine, this has been a ligand that has come up, so let's mention it. So PPH3, this is a Lewis base ligand. This is a Lewis base ligand, and what it does is it provides 2 electrons, and it turns out that it provides 2 electrons by both methods of counting. So by both methods of counting electrons from ligands, we're going to get 2 electrons. Okay, so what we do is we first look at the electrons from palladium. Now, what I always remember if I'm having trouble is that palladium is always 10 electrons. And that allows me to really understand the entire periodic table in terms of the electron counting. Palladium is always 10. Okay, palladium is always 10. And we'll come back to this. Well, I've got a periodic table open on my screen, so we'll kind of go back and forth between our notes and a periodic table just so that we can see. But if you have a periodic table near you, or if you look at one and you just Google palladium, you'll see that it's actually in the 10th column if you count from the left. So it's not like group 10, like it's 2 columns beyond the noble elements. It's in that transition metals series that bridges the main group metals, the alkali earth metals from the non-metal series. It's in that sort of bridge. And if you count from the left, from sodium being 1, you're going to get to the 10th column, including those transition metals, which has nickel, palladium, platinum, and osmium. Okay. So anyway, palladium is always 10 electrons because it's in group 10. Now, if we consider the oxidation state method, then we have to kind of think about what the oxidation state is of palladium. We'll get to that, and maybe we can go back and look at the oxidation state method of counting. But for now, we actually get to ignore the oxidation state method because we're doing the neutral atom counting. So palladium gives us 10 electrons. That's 10 electrons from the metal. The next thing that we're going to add is the ligand electrons. So ligand electrons is equal to 8 electrons. Why? Well, we have 4 times PPH3. Now, there's a lot of atoms in triphenylphosphine, but it's only the lone pair on the phosphorus that serves as a Lewis base. And a Lewis base is just something that can donate electrons to a Lewis acid. So as a Lewis base ligand, that is, it's providing its lone pair electrons to form a Lewis acid Lewis base interaction, it's going to provide 2 electrons. So there's 2 electrons per triphenylphosphine ligand. If we have 4 of them, then we have 8 electrons total. So 10 plus 8 is 18 electrons total. It turns out that palladium tetrakis triphenylphosphine, the complex that we were looking at, did I do this right earlier? Yeah, I did. Okay. Have that 4 subscript, is a 0 charge complex. So if you recall, we take the metal electrons plus the ligand electrons minus the charge, and we've got the total electron count. Well, there's a 0 charge, so we just take 10 plus 8 and then subtract 0 from that. Okay, so we have an 18 electron complex. It turns out that this complex is unreactive until it loses one of its triphenylphosphine ligands and gets down to 16 electrons. Let's look at another example and start to look at some more ligands. So palladium dichloride bis triphenylphosphine. Okay, so we have a palladium. I'm going to draw this without considering its actual geometry. So I'm just going to have some chlorine atoms and then 2 phosphine ligands, triphenylphosphine ligands. Okay. So the palladium is always 10 electrons because we can ignore the oxidation state. We have triphenylphosphine, which provides 2 electrons, and we have 2 of them. Now the chlorines actually provide 1 electron. One electron each. So if we look at this, we've got palladium, which is going to be 10 electrons. We have the triphenylphosphines, and we have 2 of them, which is going to be 2 times 2 electrons, which is going to be 4 electrons. And then we have 2 times the chlorines, which is 2 times 1 electron, which is equal to 2 electrons. So 10 plus 4, and our charge is 0. So 10 plus 4 plus 2 is 16 electrons. It turns out the palladium chloride, bis triphenylphosphine, is a bit more reactive than palladium tetrakis triphenylphosphine. And now we can see why, right? And so I'm just getting some other examples. So now we can see that we have 16 total electrons. And as a result, we now have a more reactive complex, which is again exciting to us. Okay, so we've seen 2 examples. I think we're sort of off and running. We could start to mix things up a little bit and use different metals. But before we do, I want to take a second and actually start to digest some of the ligands that we're seeing. Okay, so let's look at electron counts for ligand classes. We have seen Lewis base ligands. The way I think about these is these would otherwise be neutral. So these things that on their own, without the transition metal, they would just exist as neutral things. These are otherwise neutral, okay? These are otherwise neutral, and they donate a lone pair. And so if we have some sort of Lewis base and it sees some transition metal, it doesn't care what the oxidation state is of the metal. Turns out the oxidation state in the last 2 examples was 0. Don't worry, we'll get there. Okay, so we have Lewis base taking its lone pair and just depositing them on the transition metal in a Lewis acid Lewis base dative interaction. So these Lewis base ligands are 2 electron donors. They provide 2 electrons. Some examples of Lewis base ligands are, and again, I can't emphasize enough, the way I keep this all straight in my mind is I remember that these things would otherwise be neutral. So PR3. So we've used triphenylphosphine a lot, but it could be, those R groups could be things other than phenyl. It's just that triphenylphosphine is pretty easy to come by. Turns out, so this is, I'm going to put my name, the names next to these. So these are phosphine ligands. And sorry if you like ligands, I'm probably bothering you so much right now. Okay, there's also CO. I'm going to draw that as a Lewis structure. Now, these are CO ligands. These are called carbonyl ligands. And you're probably like, hey, that makes sense. It's got a carbon-oxygen double bond. But I want, carbonyl. I also want you to recall that all that we're using here is using carbon monoxide. That reminds me that by itself, this ligand would be neutral. Carbon monoxide can't exist. I mean, it's a heck of a ligand, which is why it causes so many issues. But it is. It's a good ligand, and it's a Lewis base ligand. So it's going to provide 2 electrons and otherwise by itself be neutral. So there is amine ligands. These also are Lewis bases, and they just provide 2 electrons. I'm looking for others, and they would exist by themselves to be neutral. But those are kind of the common ones. Now what I want to do is move into just looking to make sure. I mean, we could also have cyano. These would also be examples of 2 electron donors that are Lewis bases. We could have an aqua or a water ligand, and we could have an alcohol ligand or an ether ligand. So all of these would form adducts where one lone pair of electrons on the oxygens or the lone pair of electrons on the nitrogens, adducts with the transition metal. We don't consider any formal charges anymore, but we just know that we're providing 2 electrons to the metal complex. So again, Lewis bases provide 2 electrons. These are all examples of them, okay? Now what we have to do is be able to recognize when we have a Lewis base versus a monovalent ligand. Okay, monovalent ligands would otherwise provide or would otherwise be negatively charged. Okay, these start to get a little bit tricky. I mean, you get used to them pretty quick. But what I like to think about is, okay, if we have a transition metal adducted to our ligand, and we actually take the electrons that are bonding the transition metal to the ligand and we dump them onto the ligand, recall that we don't write the we don't really consider the transition metal formal charges. But what happens to the ligand when we put those electrons, those lone pair of electrons on it? If it's negatively charged, or actually let's write this, if ligand is neutral, then it's a Lewis base. And this is what we just went over. But if the ligand has a -1 charge, if it has a -1 charge, then it's monovalent and donates 1 electron. And so this is what we went over in the case of the chlorine atom up above. Monovalent donates 1 electron. Now again, this might just be kind of annoying because it doesn't feel too chemical. Why are we ignoring the electrons and the charge they provide in one case, that is the Lewis base? It's assuming they're not, and then treat them differently and kind of think about the charge and then change the electron count. Well, when we do that, we get to do things like ignoring the oxidation state of the metal, which can be helpful in some instances. And that's kind of what I've gotten used to. If you change the approach to start to do the oxidation state method, then the electron count lines up. So there's kind of advantages and disadvantages in either case. Okay, so what does this look like in an actual example? Well, we had discussed chlorine. I'm just going to add some more pages, sorry. Okay, so let's look at an example where we have our metal bonded to a chlorine atom. And what I'm saying is let's dump the electrons onto the chlorine atom and see what we get. Well, if we already had 3 lone pairs of electrons on the chlorine atom, and one lone pair was being used to make the bond to the metal, having that 4th lone pair of electrons is going to get us to something that's negatively charged. That negative charge tells us that we're monovalent and we have a 1 electron donor under the neutral atom counting method, okay? Whereas if we had our metal bonded to a CO like this, okay, and you could even, let's just draw it like this, a CO. And if we take those electrons and move them over, well, this is just carbon monoxide. Now, we have a CO molecule. This is a Lewis base. And remember, if it's a Lewis base, it provides 2 electrons. If it's a monovalent ligand, it provides 1 electron. Okay, so what are some examples of monovalent ligands? Okay, it turns out that there are a ton of examples of these. There are hydrides, or just H. So if H is bound to my transition metal. Halides, which is like the chlorine example. If we have X, which X could be anything, bounded to the transition metal. We could have alkyls. This is just any R group that's bounded to the transition metal, where we have just 1 carbon bound. We could have we could have alkyls. We could have aryls, which is our aromatic rings. So if we had like benzene, for example, just directly bonded at one site on the transition metal, in that case, it's monovalent, although there's a hitch in that one. There's alkoxides, and there's amides. Okay, so alkoxide would be when we've got H or R directly bonded to the H or R bonded to an oxygen, which is bonded to a transition metal. And then we have amides, which amides refers to the old school name for a deprotonated nitrogen. Okay. So all of these are examples of monovalent ligands that provide 1 electron. What I want to do is take a quick second to just kind of break down the amides and the alkoxides and compare those to amines and aguas, for example, or waters. So let's compare amines versus amides, and then maybe you'll get the point. So amines are when we have our transition metal bonded to an N with 3 R groups, whereas an amide or amide is when we have our transition metal bound to something with only 2 R groups. Now, if we dump the electrons onto both of these nitrogen atoms, we draw the result. We have a nitrogen with a new lone pair in each case. Okay, so here on this right one, we actually already had a lone pair. That's how we get an octet on the nitrogen. And so we'd have 2 lone pairs, and that would be negatively charged. Whereas with our amine, we have a neutral molecule with just the 1 lone pair. So we have a Lewis base on the left and a monovalent ligand on the right. So again, if you push the electrons over to the atom that's bonded directly to the transition metal, it has a -1 charge, then you've got a monovalent ligand. Okay, you could have other examples of this too. You could have the transition metal bonded to some sulfur atom. And that actually behaves just like an oxygen, where if the sulfur atom is going to have an octet in the original complex, we have to put 2 lone pairs on it. So after it absorbs the lone pair from the transition metal complex, it's now going to have a -1 charge and be monovalent. Okay. All right, so it turns out that there are numerous examples of these types of monovalent ligands. What we should now consider are divalent ligands. Divalent ligands have 2 bonds to the transition metal, and accepting all 4 electrons gives some R group with a -2 charge. So just like the divalent, or excuse me, the monovalent, what we do is we give all the electrons back to the ligand and see what its charge is. So the classic example is a carbene, where we have our transition metal now double bonded to a carbon atom, which has 2 R groups on it. And what we do is we sort of dump both of the bonds onto the carbon atom to give it this structure. And if we look, we've got a group 4 element, minus 2 bonds, minus 4 electrons is equal to -2. We don't usually play with this too much, -2, so we say it's divalent. And the thing about divalents is they actually provide 2 electrons. Ligands that donate 2 electrons. Okay. Another example would be a nitrene. And you could do the exact same exercise, except it's a nitrogen with a lone pair, 2 bonds to the transition metal and 1 bond to some R group. You could do the same thing. It also provides 2 electrons. So divalent ligands that donate 2 electrons. We could even have trivalent electrons. And I just want to make sure I see this. So I think trivalent you can have, and these provide 3 electrons, would be when you've got your transition metal triple bonded to a carbon, for example. Oh yeah, those are called carbines. Okay, trivalent you barely ever see. Nitrines and carbines you could see occasionally. But the next class of ligands are much more prevalent. These are pi-complexed ligands. So in pi-complex ligands, you may recall these from a the previous lecture. This is when you've got the transition metal directly bonded to a pi bond in this case. Cr2 and Cr2. Okay, we've got some alkene. These pi complexes provide 2 electrons to the transition metal. And these were awkward and new because, I mean, all the electrons are accounted for in like the second bond, but we just assumed that by drawing that line to the transition metal, we can kind of consider the that's our symbol. Okay, there's a line between the transition metal and the double bond that actually implies there's 2 electrons coming from 2 electrons that are already drawn to a pi bond to the transition metal. It's a little confusing, but my other examples, I had bonds that actually represented electrons. Here, this line connecting to the bonds doesn't actually represent any electrons. An alternative depiction, which nobody uses, by the way, nobody uses this, so I don't want us to get in the habit of it, is to draw a metallocyclopropane. And then what we could see is we've got 2 kind of monovalent ligands. That is, if you look at it this way, it's like we have 2 carbons attached directly to the transition metal. They would otherwise be negatively 1 charged. Okay, so that's one way of thinking about it. But this opens up something new that's called hapto numbers. So hapto complexes, I don't know if hapto complex is a word. Hapto is certainly a word. Hapto uses the symbol like this. This is eta, Greek eta, lowercase eta. These are, let me see if I can find a formal definition. It suggests the metal is bonded to more than 2 atoms at once. Now, there's a few classic examples of this, the first of which is allyl. So this is an allyl anion ligand. Okay, so it turns out that if you're a transition metal, you can form a bond to the carbon atom of the allyl that is monovalent. And if it's monovalent, provides 1 electron, and that's kind of the negative terminus of our allyl group. And then I did a bad job drawing that. And then what we can do is have a pi complex to the double bond. So then we have a CH2 connecting those two, right? Okay, so I'm going to put a CH2 up here. We have a monovalent ligand from the carbon atom with a negative charge, and then we have a pi complex. And pi complexes, these have 2 electrons. Now, if we do it this way, it's kind of like the transition metal is simultaneously bonded to the CH2, the CH, and the CH2. So it's bonded everywhere, or it has 3 monovalent ligands for 3 electrons total, which would be the same as if we had a monovalent plus a 2 electron. Or the best way is to just say, okay, transition metal, allyl carbons, we're going to draw a curve connecting all of the atoms together and have the transition metal connected there. And we would call this an eta 3 allyl transition metal complex, where the eta 3 represents the C atoms connected. So it turns out that we sort of exist in an equilibrium between the upper left structure, where we have a monovalent and a pi complex, and what I show is the best way, where we're actually switching back and forth between 2 equilibria. One where the transition metal is up here. We have a pi complex. And another one where the transition metal is monovalently adducted to this other carbon. 1, 2, 3, 4. Did I screw that up? I did. I'm sorry. Okay. Just right back here. I need to go directly from here to here. No. Gosh darn it. I'm sorry. Okay. Right there. 3 carbons. 3 carbons in al. Jeepers. Okay. Amateur over here. All right. So we could. So I was right at the outset. Gosh, I'm sorry. I'm going to pause for a second, or maybe I'll talk through this a little bit. But there are 3 atoms in allyl, and we can connect to one end of the allyl directly by a monovalent ligand, and then we have the double bond, which we connect to by way of a pi complex, which is a lot like just connecting to both of the atoms at once, and that is the eta 3 pi allyl complex, where we are simultaneously connected to all 3 atoms at once. Sorry for the drama there, which we show as this is our eta number, eta 3, or we say hapto 3. It's kind of annoying. Hapto is the formal language for we're connected to multiple atoms at once. Eta is just the symbol. And if we're eta 3, then we have 3 electrons because we're connected to 3 atoms. So it turns out we have some interesting examples of this. Cyclopentadiene anion actually forms eta 5 complexes. Eta 5 complexes. And this is where we saw our sandwich complexes, our ferrocene molecule. If you recall this from org 1 and 2. We're actually simultaneously connected to all 5 atoms at once. This is very common. And you could do the same thing for benzene. And in benzene, you have the transition metal simultaneously connected to all 6 atoms. And you could even have some puckering where you're on 3 atoms at once, that sort of thing. And you just pay attention to that number. It'll tell you how many electrons to consider for the neutral atom approach. If you have the oxidation state approach, then all of a sudden this number is going to increase by 1. Okay, sorry for the confusion there at the end, but pretty lengthy lecture, so I'll kill it here. And next time we'll do some more examples where we use these ligand counts to actually determine the total electron count on more complex ligands. Okay, see you next time.